In my talk, I will, in a sense, continue the theme, the topic Felix just introduced. I'll show you from a theorist perspective about basic principles of stochastic thermodynamics and how you can apply these concepts to quantitatively understand and model single molecules. And then in the second part, I want to tell you about more recent work where we discovered universal bounds on the inevitable cost of being precise in a noisy environment. And as you know, all of biology takes place at 37 degrees, at least in our bodies. So this is a quite general result, as you will see. So the basic idea of stochastic thermodynamics is roughly as follows. We all know about classical thermodynamics, which was developed 200 years ago when people wanted to understand the rules of how to transform heat into work and perhaps vice versa. There is a theory for that. It's called classical thermodynamics. And the question is whether the theory, these concepts, work, heat, entropy, whether they can be applied to much smaller objects like the single molecules. This is the Rotary machine, the F1 ATPase. And of course, yes, it works. It can be applied, and how it is applied and what you learn from this is one of the topics I'm going to show you in this talk. Now, stochastic thermodynamics is not a theory of everything, but it's a fairly comprehensive, broad theory, and it applies to all systems where you have non-equilibrium, which may be caused by mechanical forces, as you've just seen, or by chemical imbalances. For instance, this molecule can be driven by proton gradients or by ATP excess. Still, and that's crucial, absolutely crucial, all these processes take place in an aqueous environment, and therefore temperature, in the sense of the temperature, the kinetic energy of the water molecules surrounding these objects is well defined. Likewise, chemical potentials are typically well defined for molecules like ATP or phosphate or so, and this will help in developing the theory. It will put important thermodynamic constraints on kinetic rates, as you will see. And obviously we're dealing here with systems where fluctuations are important because we deal with small numbers. Now, what I'm going to show you can also be applied, for instance, for transport through quantum dots, at least as long as coherences do not play a role, but this is certainly not the topic of today's talk. And as you'll see on the next couple of slides, the main idea is that we take the thermodynamic notion seriously, not only on an average level, but also on the level of individual fluctuating trajectories which you've just seen in Felix's talk. Now, showing you the slide for the first paradigm, which are colloidal particles. Now, this has many equations, and by the way, I would also prefer that you interrupt me as you did so often and beautifully towards Felix. So the main idea on this slide is basically the one-slide summary, how you formulate stochastic thermodynamics for continuous degree of freedom, and my paradigm for that is a colloidal particle which can be manipulated by optical tweezers, as you have just seen, or this is also a nice example where you first create a periodic potential and then you drive this particle by a force also created by laser fields across this periodic potential. Now, the basic dynamical equation is an overdamped Langevin equation like we had this morning with Jean-François. So the velocity is given by the mobility times the force. That has a conservative part, the gradient of the potential, plus a non-conservative part, which is responsible for the driving, for the non-equilibrium effects. And then there is still thermal noise from the surrounding aqueous solution. Strength of the noise is given by the Einstein relation, as in this morning. And the source of non-equilibrium is an external parameter, which could in principle be time dependent, but in most of what I'm saying today, I'm just assuming I have a constant force which drives these molecules in a non-equilibrium steady state. Okay. Of course, I guess all of you know the Langevin equation has been around for more than 100 years. And it was only about 20 years ago when Ken Sekimoto pointed out that you can cast this Langevin equation in a thermodynamic form of a first law, provided you identify these three quantities: an increment in work, in internal energy, in heat. If you identify those properly, how does that work? So suppose you change the potential in a time-dependent way through such a control parameter. Then when you lift the particle, when you change the potential, this is applied work. External force times distance is also applied work. Internal energy is just the position within that potential. Now if you do the math, it turns out that this blue box works if you identify the heat as the difference, which turns out to be the total force times this displacement. Now, the key point is that all these quantities here are defined along a fluctuating trajectory. So look at this red pointer. This is a fluctuating trajectory. Along such a fluctuating trajectory, these increments are stochastic quantities. They are well defined. Now, you know from thermodynamics that exchanged heat leads to an increase of the entropy in the environment. dq is TdS. So if this fluctuates, the entropy change of the environment, or medium as I will call it, will also fluctuate. Now it turns out that this is not the only source of entropy production. You also have to assign a entropy to the system, i.e. here to the particle proper, which I call stochastic entropy. And this is a little bit formal, but you basically get it by looking at the corresponding Fokker-Planck equation, which Jean-François introduced this morning, and you look at the increment of minus d ln p, and then you get the entropy change of the system. You add this entropy change of the system to the entropy change of the environment. You put everything in the exponent. Sorry, I have to look up put everything into the exponent, and then you can easily prove that the non-equilibrium average, this is now a non-equilibrium average over given initial conditions and many force realizations, that e to the minus delta total entropy change, that this is always 1, even under non-equilibrium conditions. And from this, you get by Jensen's inequality, you get that the average change of the total entropy has to be positive. Now, if you want to prove that, the best way of proving it is using the path integral representation for this dynamics, and then it's not more than 8 lines. I leave that for you as a homework problem. Now, perhaps an important point here is, have we proven the second law? I don't think so, because we have put in basic irreversibility at the very beginning. If you write down a Langevin equation, you have written down an irreversible phenomenon from the very beginning. You should not take this, as it is sometimes claimed, as a proof of the second law. Okay, so this is the one-page summary, and of course, the literature you find reviews and many places where all this is developed in detail. Let me show you other variants of such exact relations. Perhaps the most famous one is the Jarzynski relation, which tells you that if you look at the non-equilibrium average of the work, in case where you start in a thermal initial condition, so this is kind of more restrictive, you're also not allowed to have non-conservative forces for the Jarzynski relation. But in such situations, you can extract the free energy, which is an equilibrium quantity, from a non-equilibrium average. Or if you compare, like in Felix experiments, work distributions of forward and backward folding and unfolding path, you get what is called the Crookes relation, from which you can extract free energies very precisely. And again, I want to stress that these are mathematical identities. There's nothing to test about. These are theorems within both stochastic dynamics, as I just introduced for Langevin, but also Hamiltonian dynamics. If you imagine the whole aqueous solution, if you imagine that you include this aqueous solution, you can prove that whenever the initial state is thermalized. So this is the one big class of systems we're interested in, systems with a continuous degree of freedom. And I've shown you the equations for a single degree of freedom. Everything holds for many coupled degrees of freedom. like Jean-François had this morning for many, let's say, colloidal particles. Now, if we want to understand biological systems, we will have to deal with the fact that they are often driven to non-equilibrium because of chemical reactions, because ATP is used. These are chemical reactions, so we need the same thing, same concepts for the case where we have discrete states and chemical reactions. So this is on this slide. This is an enzyme, theorist's view of an enzyme, which has different states. And there are transitions between these states which may or may not involve chemical reactions, like, for instance, ATP being hydrolyzed to ADP and phosphate. So we have this kind of chemical chemical reaction. Each of the enzyme levels has a free energy, which obeys this usual thermodynamic relation. Now, if you're looking at the rates for forward and backward transition, you cannot choose these rates as you want. This is one point where you have to be thermodynamically consistent, and thermodynamics imposes that the ratio of these rates depends on the concentrations, i.e. on mass action law, kinetics. And then thermodynamically consistent rates imply that the log ratio of these rates is given by the chemical potential difference for these chemical reactions and the free energy differences of the two involved levels. And then, for instance, you have a first law for this transition. There is obviously no work, but if the enzyme jumps from here to there, it has a different internal energy, and then there will be some heat dissipated in a reaction. So we're now talking about heat dissipated in a single reaction event of one molecule, one ATP hydrolysis. The change in internal energy is the change in the energy of the enzyme, but if you have a chemical reaction, the internal energy in the solution will also change. There is this heat associated with this transition, and then when you combine things, for instance, you see that the delta mu is given by this heat and the energy change of the enzyme and also the delta S of the solution. So the basic message I want to convey is we have now defined consistently the thermodynamic quantities from the early 19th century, and we can apply them to systems which are accessible by the experimental techniques of the 21st century. And now I want to show you one example how that works. And this is about this rotary machine. So again, here is the molecule. So people typically look at this F1 part. Who's seeing the F1 here, or the F1 ATPase for the first time? Okay. Minority. So let me explain it. So usually this molecule is used to synthesize ATP, and then it's driven by these proton gradients. But you can also isolate that part. You put it on a cover slip. You provide ATP in excess, and then this molecule can go into a kind of rotary motion. So what precisely happens is that this purple subunit gamma, it changes 120 degrees with each hydrolysis event. Of course, you can't see that single part of that molecule, so what you do experimentally, you attach big beads to it, and then when this gamma turns around 120 degrees, this big thing turns around 120 degrees, and this you can measure optically, and then you can plot the angle as a function of time, and you get these kind of traces. These were mainly Japanese school who did that first. So the blue case is when you see clearly single steps of 120 degrees. When you provide more ATP, the whole thing runs faster, and then you get these kind of red traces. Now, the key point is that you only see the motion of this probe. This will become important. You do not see the very part of the molecule. These steps of the motor are hidden. You only see what the signature of these steps through the motion of this probe particle. But then questions you can raise is, how is that kind of visible kinetics here related to thermodynamics? What about the first law? In a sense, I answered that before. And also, what about the efficiency of this machine? When you let it run against an external torque, then, like in Felix experiments, it can run against an external impulsed force, or torque in this case. And then you can ask, how efficient is that as an engine? It uses ATP, it delivers motion against this force, so efficiency as output divided by input is well defined. Now, before I show you experimental data, let me show you the arguably simplest model for describing this. And again, I insist you have to keep track of at least 2 degrees of freedom. One is the probe particle, one is the motor. Let me first map this rotary motion to linear motion, which is kind of easier to draw. Then the situation is as follows. There is this big probe particle to which an external torque or force is applied here to the left. The motor, which would be this gamma subunit, has discrete steps. This would correspond to 120 degrees. And each step is associated with the hydrolysis of one ATP molecule. So what happens if the motor undergoes a step? The blue particle will be sitting here. The spring is loaded, and then the speed will follow. And remember, what you see is the trace of the bead. So the bead is big enough to be modeled by an overdone Langevin equation, as we had before. We have to assume some coupling here, in the simplest case harmonic. And the motor does discrete forward and backward jumps. Again, you can't choose them as you want. The ratio has to obey what is called local t-state balance. So it has to obey, essentially you have to put the free energy difference in the exponent, which has 2 contributions. One is the delta mu of the hydrolysis reaction, and the other is the difference in the elastic potential. Everything clear so far? Yes?
How do you apply this external torque to it?
Excuse me?
How do you apply this external torque to the speed?
To the speed?
The bead.
Oh, to the bead. Well, this is done by electric fields or by magnetic forces, right? That's an experimental question. You do it by electric fields or by magnetic forces. You should ask Felix in the break how you do that. For the theory, it's completely irrelevant. But I'm happy to hear that everything in theory is clear. So. No, it's good, but I can't say more. I didn't do the experiment. Okay, looks like a very simple model, but still you can't solve it analytically, even if that's a quadratic potential, but you can easily throw it on the computer, and then you get traces like this. Now you see the advantage of the theory, of the simulation compared to experiment, is that you see both. You see the probe particle and the motor. So take this red trace, that's the position of the motor, and here it jumps, and the fluctuating trace is the probe particle. Interesting, it's a little bit weak here because you have too much light, but for instance here you see the motor jumps, but the bead doesn't follow, so the motor has to go back, and only here when the motor jumps the bead follows. So basically we get the same traces as the experimentalists get from their data. For instance, we can now also get the distribution of the distance between motor and bead on average. The blue trace is the faster trace here, so when the motor is faster, it's typically almost 1 step ahead of the bead. That's why you get this kind of shoulder here. Now, again, a summary of the first law for this situation. The first law has 2 contributions. So suppose the probe particle moves a distance delta x. How does the first law look like? Then we have work against the external force. If the probe particle moves, we have some heat associated with that motion. And of course, we have a change in internal energy because that spring is loaded. Now, what happens if the motor moves 1 step? There is no work. There is heat associated with this chemical reaction. There is a change in the length of the spring. And because we have a chemical reaction, the internal energy of the surrounding solution has changed. We have one less ATP and we have one more ADP and PI. That changes the internal energy. Now, if you now average these two relations, you sum them, you're here, and then you massage them a little bit, and then you get how this is typically written. So delta mu dot is the input of chemical work. That's the mechanical output. That's what you get. And on the right-hand side, you get the heat released due to the pro-particle, due to the motor particle, and there is also an entropy change in the surrounding solution, and it turns out that you can't distinguish these two terms. But this is now the basis for getting the efficiency. Now there are, since I'm in Paris, I like to show this slide. There is a thermodynamic efficiency which was introduced here by Jacques Proulx's group. So the efficiency, if you have an applied external force, is just the output divided by the chemical input. Now I'll show you data from this Japanese group where they even look at something which they called efficiency if you have no external force. So what did they say? Well, they said that whenever all the free energy associated with the reaction here is used to load that spring, we call that efficient, because ultimately that's what the motor should do. It should use that free energy to load the spring in order to store that energy, and then of course the beat at some point will follow and will just dissipate this energy. So they have defined what we then call the pseudo-efficiency, which is the heat released by that probe particle divided by the chemical input. We call it pseudo-efficiency. It's hard to see here because these are data for our model. You can easily get into a situation where this is larger than 1, especially at small delta mu's, and therefore you should not really call it the thermodynamic efficiency. But it's a quantity they looked at. So how did they measure these quantities? Again, through another relation, which is called the Harada-Sasa relation. So here you see the correlation function, and here you see a response function. And you should know that in equilibrium, correlation and response are related through what is called the fluctuation dissipation theorem. So usually in equilibrium, that would be 0. What Harada and Sasa had shown is that you can actually get the entropy production, or here the heat released through the motion of the probe particle, by looking at the violation of this fluctuation dissipation relation. So what they did experimentally is first they measured the fluctuations of this motion as a function of frequency, and they also measured the response, which means they had to apply an additional little torque. And then they look at this area in this integral, which is this gray shaded thing, and from this they get that. And then using this, and this will be my last slide here, using this, they could measure this heat, and also if they apply an external torque, they could measure the work. They did this for different concentrations of ATP, ADP, and phosphate. And they compared with the delta mu of the hydrolysis. So they got typically this kind of diagrams. When we use our very simple model, look at the same quantities, we get essentially the same data given the error bars. That's a very reasonable agreement. And I'm just using this to convince you that even with such a simple model, you can reproduce or represent experimental single molecule data more or less faithfully. Okay, I'm doing time. Oh, that's fine. Okay, so now I want to show you another question for this particular molecular motor experiment, which appeals a little bit to this idea of having different scales or different degrees of freedom, because I emphasize so much that you have to keep track of both the motor and the probe particle. I want to show you what happens if you don't do that. And most people don't. And that's what we call coarse graining of such models. And let me first explain the basic idea using the simplest case. So this is what we just discussed. Now suppose I'm lazy and I want to model this just with a single degree of freedom which jumps back and forth. That's what people usually do. Okay, so for this I use the capital omega rates. Now, I believe in this model, so the question is, what is the best omega model? What is the best coarse-grained model I can do? I have to impose conditions, and I think two conditions are reasonable. First of all, I want to have the same mean velocity. And of course, in this case, the mean velocity is just the distance times the difference of the rates. And then, because I want to be thermodynamically consistent, I want the ratio of these capital omega rates to be given by the chemical potential difference. And if I apply a force times distance, I have to put in the exponent. That's a kind of minimal requirement. Okay, these are two conditions, two unknowns you can easily solve. But here comes the key point. Now we look at how these coarse-grained capital omega rates depend on the force. So if you use that prescription to calculate them, let me show that. We now calculate the omega, for instance, the omega plus as a function of the external force, likewise the omega minus. And you see for fixed probe particle diameter and the measured elastic constants, you see that these rates are anything but exponentially dependent on the external force. Usually, however, that's what's usually done. So that's a scheme I just described. But what is traditionally done is you use rates where you put the force into an exponent with what is called load sharing factor theta minus and theta plus. So in that case, the force dependence of the rates is mono-exponential. If you did it correctly, I think you would have to do it like we did here, and you would get vast differences as a function of the applied force. And you see, this is logarithmic here, so this is really enormous differences. These are several orders of magnitudes. And this is not just a feature of the simple model. We checked the same thing for a little bit more involved model. This is this kinesin from Lipovsky's group. So you have this kind of 6-state model. We did the same thing, and again we find that the force dependence of the coarse-grained rates is, can be non-monotonic, well, not quite non-monotonic, but you can have different curvatures, positive curvatures, negative curvatures. You even find that the stall force depends on the probe size when you do the full model, which you would never get in the simplified model. So the message here is you better keep the probe particle. Okay, so much as a kind of extended introduction. I've introduced the principles. I've shown you how you apply these ideas to molecular motor models, and I'm advocating here to be more honest in the modeling and keeping the probe particle. And I want now to move to the second part of the lecture, which is about the role of precision and the cost of precision. And in order to introduce this, I want to show you on the next slide something extremely simple, something all of you know, but you will see it in a new perspective. So let's look at a random walk, an asymmetric random walk. So imagine you have this kind of trace and you step preferentially to the right. And of course you could think of a molecular motor, but it would hold for any other system as well. And let me run you through these 6 lines because it will be crucial for whatever will follow. I want you to think of that as a process which has an output. And the output of that process are steps. And suppose on average I do 1 step per second. I have an output which is given after time t. I have stepped x steps. So I can write that as a current, which would be a velocity times the time. And that's of course just the difference in these rates. Now when I run that for a fixed time, fix the time, so you run it for a fixed time, the actual output, suppose I do 1 step per second on average and I run it for 10 seconds, will not always be 10. Sometimes it will be 11, sometimes it will be 9. So the output of that process comes with a certain variance or a certain uncertainty. And of course, a measure of this variance is this expression, which is just the diffusion coefficient, right? So that's the sum of the two rates. So the uncertainty of the output in a dimensionless form is given by that variance divided by the output squared, and that's given by this relation, again, J is the current, i.e. the mean velocity. So far, so good. Now comes the thermodynamic part. If you want something to step preferentially to the right, you have to pay for that. You have to pay for breaking this time reversal symmetry. So there is some thermodynamic cost associated with it. So in the molecular motor, it's the free energy of the ATP hydrolysis. Generally speaking, the cost is the temperature times the entropy production times the time, or the velocity, times the driving force, which is called affinity, times the time. So what is this affinity? This affinity is given by the log ratio of the rates, and if you work it out, it's just, again, the delta mu of that hydrolysis step. You have to provide the ATP at high chemical potential for the whole thing to run to the right. Now you combine all this relation, and you find what I found intriguing when I saw this. The cost times the uncertainty squared is given by this function, which is always larger than 2 kBt. Which means that if you want to have a very precise process, i.e. a small epsilon, you have to pay more. Higher precision comes at a higher cost. Now you could say this is just a feature of this simple asymmetric random walk, but I will now convince you that this is much, much more universal. Essentially, it will hold for any process. So how did we get to this? And this is now work involving my former postdoc, André Barato, who's now in Dresden. First, and we call that relation thermodynamic uncertainty relation. First, we looked at general unicyclic processes. So suppose you have 6 states, and you want the system to run through that 6 states as precisely as possible. So if you count only full revolutions, we have the same quantity, the epsilon squared. So what about the cost? Now in this case, the affinity is given. In the former case, we had just the ratio between, log ratio between backward and forward rate. In this case, you have the log ratio of the product of all forward and all backward rates. We have green and states. And you can show, this is what we had proven, you can show that again you have an inequality of that type, which now involves the number of states. But again, it's larger than 2 kBt. And both of these bounds are sharp. The first one saturates if all the forward rates are the same and all the backward rates are the same. The second one saturates if you're close to equilibrium, i.e. in the linear response regime where the affinity is small. In that case, of course, you only weakly break the asymmetry, so you have the lowest cost, but of course to get a certain output you also have to run it longer. What about more complicated processes which are certainly not unicyclic? So now you take just any network, any number of cycles, any connectivity, topology, whatever. The point is that you still have this fundamental relation. And to relate it to some numbers, suppose you want a process which is sharp on the level of 1%. Perhaps this is not too much to ask for, but this relation will tell you that whatever you do, however you wire your molecules, you have to pay at least 20,000 kBt. So why is that unicyclic result also valid for multicyclic cases? The physics, in a sense, is that if you add more cycles, you basically increase fluctuations, i.e. the uncertainty, without really gaining much. I should say that we had proven it in linear response. We did a lot of numerics for various networks, but the full mathematical proof, which is anything but trivial, I'm not going to show it here, was found by the MIT group a year later. It's based, I should say that it's based of using large deviations on the level 2.5 for the experts. It's a highly non-trivial result, the full proof. Okay, so you can imagine that this has presumably, yeah, before I tell you about applications, is the statement really clear? I mean, it looks so simple, but I think it's really deep. Two questions, one in the back.
How do you relate that to some kinetic proofreading, which is a kind of mechanism which...
Yeah, that's a good question. What about kinetic proofreading? So I'm talking about precision here in the sense of an outcome as I had defined it. I'm not talking about building in the correct molecules versus the wrong ones. You see, that's a kind of binary decision, which is a different setup from what I'm talking about here. There was another question?
Well, what's precise about this thing? I mean, when we talk about precision, you are saying it's about measuring x in this case, right?
Yeah.
Almost.
Yeah.
But x is any observable? Is any?
Yeah, it's an observable. I mean, you see, here is the definition. I mean, you measure the mean, and you measure the spread around the mean, and you can do that for your helicases. On the next slide, I will show you something which will hopefully truly impress you. So that's why I want to make it clear that everybody in this room has understood. If you take if you want to take home one message from this talk, is there is a fundamental cost to precision in this sense. Okay, so let me show you two consequences of this result, and I'm sure we haven't not yet even thought about all possible consequences. Suppose you have a molecular motor, molecular machine, and you don't know how it's wired. So you have something complicated which is running along this track against a force. A simple consequence of this uncertainty relation is a relation a bound on the efficiency of this motor. Efficiency, as I said, is output power divided by input power. Output power is force times velocity. Input power is how many ATP molecules you use per time. And what I can show is that this efficiency is bounded by this function, which involves only measurable quantities. So it's less than 1 over something which is larger than 1. And this involves the velocity of this motor and the diffusion coefficient of this motor, which you can easily measure. You can measure both of them. And then, without knowing anything about the mechanochemical cycles which are hardwired into this motor, you can predict that the thermodynamic efficiency is less than this function. And when I saw this, I was really impressed. And here is an example. I take this simple model. Here is the force now in units of force times distance over delta mu. So the simple unicyclic motor has a very simple efficiency, which is just linear in the applied force. So here is stall force. There you have efficiency 1. But if we now take this model and we determine in a simulation or analytically the velocity and the diffusion coefficient for different values of the delta mu of the hydrolysis, we get these kind of bounds. You know, these bounds may not be perfect. So the true efficiency has to be below these colored curves. Of course, in the simple model, we can get the true efficiency. So you see there are cases where the bound works rather well. There are other cases where the bound doesn't work so well. But if you have an unknown motor or helicase, whatever, you measure the velocity, you measure the diffusion coefficient, the applied force you know, you plug that in, and you get that. Why do you get that so easily? Well, this efficiency is related to the entropy production. The entropy production is the power in minus the power out, and therefore you can transform this cost relation within 3 or 4 lines into this relation. Any questions to this result, which I think all experimentalists should jump on, look at their old data? Of course, you take your old data, plug it in, you make a prediction of how efficient your helicase is.
For example, there are experiments already. I mean, many experiments have been done on motors.
Yes.
In kinesins, in dyneins, myosins, and people have measured the speed of the motor.
Yeah.
They have measured, the diffusion coefficient, D.
It's harder.
That's harder, but probably there are estimates.
Yes.
on this. And have you tried to?
Not yet,
Because
not
it's
yet,
published out because-
not yet, but look at this. This is only 2 months.
What? Oh, the publication. Okay.
No, it's not even published
Well,
yet.
no, 1 more, 2 more. Okay.
Okay, so yes, but of course I would be even more interested to be involved with real data, which may not have been published yet. Okay, so this, yeah, please.
Yes, so a very general question, I guess, for any kind of machine is what kind of relation there is between power and efficiency. And so I was wondering, do you think that the uncertainty relation can answer this question?
No.
Give some bounds on that.
Okay, no, I mean this is, you see, the most fundamental quantity from a thermodynamic perspective for any machine is its efficiency. Now, as you know, for instance, thermal engines are bounded, heat engines are bounded by the Carnot efficiency. However, a heat engine that operates at Carnot efficiency is useless because, as you say, there is no power. And for these isothermal machines, all biological machines are isothermal, 37 degrees. The bound is always 1. That's what replaces the Carnot. Now, making universal statements about bounds on power is much harder for the following reason. Efficiency is a nice quantity because it doesn't have a dimension. If you want to make universal statements about power, and we have done that, especially for thermoelectric machines with Kai Brandner quite a bit, you first have to somehow normalize the power to something. And then it's typically known that when you plot the power as a function of the efficiency, either efficiency or for thermal engines, efficiency over Carnot, so typically you get curves which look like this, or perhaps like this. And then there is something what is called efficiency at max power. And some people claim that you can get universal results on that, but it's much more, these are typically much weaker statements because you have always to say in which parameter space do you maximize. And there are at least 40 papers from the last 10 years, including 5 of us, on this topic.
Sorry, why is the power not F times V? In your
The power is F times V.
So it's used in the definition of your efficiency.
Yes, but so my efficiency is the power out, which is F times V, divided by the power in, which is the number of chemical delta mu I burn per unit time. But you see, usually the problem, of course, is this V, of course, is a function of the force, and it's a function of the delta mu. So that's where all these nonlinearities come in. And I mean, here you get a simple line for the efficiency versus force because it's a unicyclic motor in our simple model. But the statement is that even if that motor was not unicyclic, and even if you didn't know the precise wiring and all the mechanochemical cycles, this relation is universal. Yes?
If you have more than one motor,
Oh, it holds true even for motor complexes. Yes, yes.
Sorry. So there are some non-canonical helicases that people have argued that don't use ATP for unwinding. I mean, they just melt 2 or 3 bases and then unwind short duplexes. How do we define the efficiency in those cases?
Okay, so I'm talking here about steady state situations. So I'm talking about a molecular motor which is in steady state. I mean, steady state could involve, of course, periods of pauses. It could even involve detachment and reattachment, because even I could include the detached states in my network. But you have to do it under steady state conditions. Maybe something even for transients, but that's a different story. It's proven for steady state. Was that the question? Okay. Okay, so let me show you the second consequence. Suppose you have an enzyme and you don't know the enzymatic cycles it's operating on. And again, I'm using a simple example. So I guess who doesn't know about Michaelis Menten? Okay, 2 people. Let me explain Michaelis Menten. Michaelis Menten is the upper triangle. You have an enzyme, E. The enzyme can bind a substrate. Then the substrate can be transformed into a product, and the product can be released. That's the simplest enzymatic scheme. That's the upper triangle. However, you may have a more complicated scheme, or an enzyme which can bind 2 substrates, can transform the first, can release a substrate, or can transform the second substrate into a product, and then release one, and then release another one, and so on. Now, what people can measure, and this is a whole field, I think it was Carlos Bustamante who introduced that notion of statistical kinetics. Suppose you can measure the outcome, the production rate of a single enzyme. You measure the number of P's you get per time. And then you look at something which is called the Fano factor, which is again this variance, but this time you don't divide by x squared, you only divide by x. What we can prove, and again it's a kind of a variant of what we had before, we can prove that this is bounded by a function like here. A is the affinity. So the affinity is what this enzyme uses for this kind of transformation. So in the simplest case would just be the delta mu of the hydrolysis. And M max is a kind of characteristic number for the network. It's that number which involves the largest, the cycle with what I call the largest effective length. Effective length is the number of states divided by little n, which is the number of products in this cycle. So for instance, for this cycle you have 3 states and you get 1 product. So capital M is 3. For this big one, capital M is 6 divided by 2, which is also 3. However, in this network, you have a cycle which consists of 5 states and where you get only one product. That would be the largest number. So since the Fano factor is bounded by this quantity, you can actually get, by measuring the Fano factor, and by knowing the affinity, the delta mu of the hydrolysis, you should typically know, you can get a bound on this Mmax. And this you can then use as a diagnostic tool for inferring an unknown underlying topology of your reaction network. So in this particular case, suppose you measure a Fano factor of 1/2. Suppose you provide a delta mu of 4.5 kBt. Then this bound tells you that the Mmax has to be larger than 3, and then you can exclude a simple Michaelis Menten scheme for the enzyme, just on the basis of experimental accessible quantities. You measure the Fano factor, you know the delta, the A, i.e. the delta mu. You look at this, basically, if you have this curve, there is one region is forbidden, and on the basis of such a statement, you can exclude certain network topologies. Okay? And so these are just 2 examples which we have worked out so far, but you can easily imagine that you can do more things using this kind of approach. I don't know who has seen, last week we've posted a longer paper where we determined the inevitable costs for a precise Brownian clock, which is just another variant of this motif. Okay, so this would have been 45 minutes now. I can either stop here or I can tell you about 5 more slides about stochastic thermodynamics in the context of sensing.
Well, maybe you can see if we've got some questions so far. More questions? There's one over there.
Excuse me, about the first one.
Yes?
You told that there is a universal bound on the efficiency, but is this about the average efficiency or the efficiency of a single trajectory?
No, this is the efficiency in the sense of the average. This is the efficiency in the sense of the average output divided by the average input. Okay? I'm not talking about what some people call stochastic efficiency. Yes?
Yes, so recently there were some reports about protocols to get very fast equilibration from one state to another.
Yes.
A lot faster than the relaxation time. And basically they use a protocol in which they really confine the phase space. Is this something we can understand in terms of your uncertainty relation?
I don't think so, but I think you can understand that using the concepts of stochastic thermodynamics, and we have partially understood that 7 years ago. So the question is or a variant of that question is the following. Suppose you have initially given a potential and you have a thermal distribution here. And suppose your goal is to get this distribution at the end into such a potential in finite time. You want to go from here to there in a finite time delta t, and you want to do it as a minimal thermodynamic cost or work. This is what is called optimal protocols, which is related to what you're saying.
You want to do it in much shorter time than the relaxation time.
Yeah, sure. I mean, so suppose you would instantaneously switch this potential to this potential, you would have to wait for the relaxation time, right?
So what you see is that if you want to do it a lot faster,
you have to manipulate the potential accordingly.
Oh, yeah, but so there's a cost to it, and I was wondering,
Yes.
since you're manipulating a current to
Yeah.
follow your exact protocol, isn't that more or less what you're doing, because it makes your current more distant or your position obsessed?
No, but you see, what I'm telling you here is what I have been telling you here is about stationary states. I don't have any time dependence in my external parameters up there. Here you're talking about things under time-dependent protocols, and for that you have to use what I introduced on the first part in my talk. And what I'm telling you is that, I mean, we and others have looked into this. We introduced this with Tim Schmiedels in 2007 in a PRL. The question was, how do you go from a given initial state to a wanted final state in a given time at the lowest cost? Now, if this time is less than your relaxation time, obviously, this is your question.
Well, so I know it costs more, but so I was wondering
how much more it costs, whether there are bounds.
And I mean, if we can think, I mean, of course, your current equation is for stationary states.
Yes.
Okay, can we think of extending it to the switch process, because it talks about a certain precision of protocol?
Yeah, I would not be surprised if one could, but I certainly can't at the present moment. Okay, but I know it's a whole, especially in quantum mechanics, it's called shortcuts to adiabaticity. It's a whole new field. Yes, I know. More questions?
So I propose that you proceed for maybe 5. Can you do it in 5 minutes or 5-10 minutes?
I can do it in 7 minutes.
7 minutes.
Okay, So what is the problem? I guess you will hear more about this, and there are experts in the room who know much more about it than I do. So if you're bacterium, and if there's a region where there's a lot of food, you want to swim there. In order to make this decision, you should at least know perhaps your present concentration. And for measuring a concentration, the bacterium has a whole machinery, biochemical machinery. And as I said, I mean, there's a huge literature. I'm interested in the one aspect you can address using the concepts of stochastic thermodynamics, and that is the following question. Forget about all the spatial degrees of freedom. So suppose you want to measure something which is time-dependent, a time-dependent concentration, and assume that this time-dependent concentration has just given some external process, could be the concentration of a nutrient, I call it x of t. You measure that, basically you measure the time receptor, you respond it, and then there is this downstream machinery, and at some point you store that information in some internal variable, which is typically the concentration of some phosphorylated protein. And the simple question we asked some time ago is whether there's any relation, and therefore it appeals to this precision issue also, is there any relation between the rate of information acquired about this external process and the cost of maintaining this very machinery which does the measurement? That's a general question, and you might suspect, yes, there is a relation. The more precise you can measure, the more you have to pay for your machinery who does that measurement and storing. Okay, that was the naive question. Of course, it's a complicated problem. There's a whole hierarchy of layers or players. There is the external concentration, which in the simplest case switches between high and low. Then a ligand may be bound or unbound. Ligand may bind or not bind to a receptor. The receptor may then be active or inactive. If you're dealing with adaptation, there is a methylation level of the receptor, and then there is at some point a downstream protein which is phosphorylated or dephosphorylated. From the thermodynamic perspective, it's important to know whether which of these processes requires free energy in the sense of which is active, i.e. needs ATP for its functioning or another molecule. And certainly those here are. Binding, unbinding is just a kind of equilibrium process. So in order to answer this question I had on the previous slide, you need a framework, and the framework we developed is what we call Stochastic Thermodynamics of Bipartite System. And that's the kind of general framework which you can apply to many situations. So what is the idea? The idea is that you have an external process which jumps between different states. This could be high and low, or high, middle, low. And these jumps are independent. In the simplest case, this is just a Markov process between different values. However, your internal world, your machinery, has also different states, but now the transition rates between these states depend on where instantaneously the external world is sitting. So the internal jumps, ij, are affected by the current state of the external world. We did that in this way because then at the end the whole thing is a nice non-equilibrium steady state which obeys the usual rules of stochastic thermodynamics, i.e. has a positive entropy production, and that has two parts, the one associated with the external world and the one due to the internal jumps. And when looking for a quantity which is bounded by the dissipation due to that machinery, we found what we then call the learning rate. The learning rate is the decrease in the Shannon entropy about the state of the external system. You want to know that state, and therefore you have jumps here in your internal world, and the precise definition for the learning rate is that it's the change of this Shannon entropy, the conditioned Shannon entropy. And what you can prove is that this learning rate, again, is bounded by the entropy production associated with this machinery. And then you can define an efficiency of learning, which is just the ratio. My initial guess was that the rate of mutual information was bounded by the dissipation or by the entropy production, but that turned out not to be true. And here on my last slide, I'm showing you just again, this kind of simple case. So from all of these layers, we just use one, an effective one. So the internal state, the protein is either phosphorylated or not. Then there's the external concentration. We're just switching between high and low in a kind of Poisson process. And what we want is that if the external concentration is high, the protein is in its normal state. And when the concentration switches to low, it gets phosphorylated and then it ends up in this Y star state. So again, in this non-equilibrium steady state, at the end, we want a high probability here on the diagonal, so that by knowing the Y state, you can infer the external state, and a low probability on the non-diagonals. Again, you do it thermodynamically consistent. The rates are not arbitrary. The delta mu comes in. You can solve it analytically. You plot diagrams like this. Let's just take this one. This is the efficiency of learning as a function of the rate with which the external world switches. So if the external world switches slowly, you get a high efficiency. You can even approach 1. If the external world switches too fast, this internal process cannot follow. And in this case, the efficiency goes down to 0. This is a very simple case. We did more involved cases using these several layers. We also did it with adaptation. The message for today just is you can use also this machinery to talk about a different kind of precision. This is now precision in measuring an externally changing signal. Okay, so let me close here. I hope I made it in these 7 minutes. And I hope I've shown you, using various examples, that this is a very versatile tool using the stochastic thermodynamics to quantitatively model and understand biological non-equilibrium processes, mostly on the molecular level, but perhaps via coarse grading in the future also towards the cellular level. Thank you very much.